We're now at the point where we've separated the hydrogen atom problem into two parts, one of which, the centre of mass motion of the entire hydrogen atom as a unit, we have already solved. It was just like a free particle with a mass that was the sum of the electron and the proton masses. Now we're going to start solving properly for what we can call the internal states of the hydrogen atom. These are the states we're used to in atoms with orbitals and discrete energy levels. We've already separated the overall Schrödinger equation for the electron and the proton into our two separate ones, the centre of mass motion one and the internal state one. Now we're going to be separating the internal state equation itself into two parts, an angular part and a radial part. The angular parts we've already solved. These are the spherical harmonics. So once we formally perform this separation, we will be concentrating on the solutions of the radial part of this equation. So let's look to see how we solve for the well-known atomic orbitals and energy states of the hydrogen atom.
So let's start to solve properly for the internal states of the hydrogen atom. We start with the equation for the relative motion of the electron and the proton that we already worked out. So here is the equation, del squared with respect to the relative position of the electron and the proton, and our potential here, which is a Coulomb potential, and though we've written it as a function of vector r, really it's only a function of the relative position distance, the ordinary scalar r. And we use the spherical symmetry of this problem that we know of, and we're going to change to spherical polar coordinates. And also from this point on, because we know we're only working in this set of three coordinates given by the vector r here, we're going to drop that subscript. So in spherical polar coordinates, the del squared operator looks like this rather forbidding formula here. The term in square brackets, though, is one that we've already seen, and that's this operator that previously we called del squared theta and phi, and it's really just the L squared operator with this minus sign and the h bar squared on the bottom. And we introduced that in discussing angular momentum. Knowing the solutions to that problem, which we worked out, they were the spherical harmonics, for example, we're going to propose a separation. We're going to propose that this complete wave function, u of r, for the relative position of the electron and the proton, is some product of a function only of the scalar distance r between the electron and the proton coordinates, and a function of angle. Now, of course, this is actually going to turn out to be our spherical harmonic function that we already worked out. But we propose this separation, and as usual with these separations, the only justification for them is, in the end, that we find they solve the equation with sufficient generality for us. So at the moment, this is merely an intelligent guess that we could manage to factorize the function in this way. Now, the mathematics of this is much simpler if we make a minor change. If we use this form with 1 over r times some other function we're still going to figure out, here we've called it chi of r, instead of the r of r, the capital R of r that we had before. And obviously, of course, this function chi of r is simply related to that previous function we proposed. Chi of r is equal to little r times capital R of little r. The reason for doing this is it greatly simplifies the form of the radial derivatives that we have to use in practice. So all of this complicated expression here that came from our del squared operator in spherical coordinates for the various derivatives associated with little r, when we use this chi of r over r function for the capital R, then this greatly simplifies. All of this here just turns into this rather simple expression over there. Hence, our Schrödinger equation becomes this expression here. Here's our 1 over r d2 by dr squared. This was what was left of the radial parts of the del squared operator. Of course, this is operating on the product of chi of r over r times y of theta and phi, but nothing in here involves theta or phi, so we can take the y of theta and phi outside. Similarly, this is the part that was all of the angular derivatives. We're now rewriting it in terms of this L squared operator we figured out before, and it only operates on the angular parts here, and we can take the purely radial functions outside. And this is the entire wave function multiplying the potential, and this is the total energy multiplying the entire wave function. So this is our Schrödinger equation slightly rearranged as a result of our separation proposal. If we divide both sides of this by this factor here and do a little bit of rearranging, then we get an equation in this form. What we've done here is we've taken the terms in EH, the total energy, and moved those over to the left, and we've taken the terms in theta and phi here and moved those over to the right. So in this equation, in the usual manner for a separation argument, we note that the left-hand side depends only on little r, in fact it depends only on the scalar r here, and the right-hand side depends only on theta and phi. So both sides must be equal to a constant, the separation constant. And we already actually know what that constant is, since we know how to solve this particular eigenequation. We know what all of this here has to equal. That is, we know this solution already, and so this constant has to be L into L plus 1. So in addition to the L squared eigenequation that we have rediscovered here, and we've already solved this one, we also have this radial equation, and we can rearrange that slightly into this form here. And we can see that this is an ordinary differential equation now. There's only one variable in here, little r, and so we can go back to looking at ordinary derivatives, not partial derivatives. Hence, we have the mathematical equation that we can write out here. And this looks like a Schrödinger wave equation. Now, of course, we are solving a Schrödinger wave equation, but this is not the total wave function we're really solving for. It's only part of it. This statement here is a purely mathematical statement that this equation here actually looks very like a conventional Schrödinger equation, but with an additional effective potential energy term in here of this form. Now, as I say, this is only a mathematical statement, but actually if we were to try to solve this equation now from first principles, we could in fact use some of our understanding of what it's like to solve Schrödinger-like equations to solve this with an effective potential energy in it. Note incidentally that in this equation we've got a specific form for V of r. It's our Coulomb attraction between a simple electron and a simple proton. And that gives us our assumed Coulomb potential like this. This separation is going to work for any potential that is only a function of little scalar r here. There's nothing in the arguments we put together so far for this separation that required any particular functional form here for V of r. What was important was that the potential only depended on the scalar distance between the electron and the proton. A potential like this is sometimes known as a central potential, even if it does not have this particular form. And the precise form of the equation that we have here, and this potential is just arbitrary in here, will be different for different central potentials. In other words, we would have different potentials in here under different sets of conditions, but the separation would still be possible. We would still be able to separate out the L squared angular momentum eigenequation. Now, why does this matter? Well, it matters because this could be a reasonable first approximation for more complicated atoms. That is, we might reasonably presume as a first approximation that even if we've got a more complicated atom with lots of electrons and lots of protons and neutrons in the nucleus, that to a first approximation the potential energy might still just be approximately dependent only on the magnitude of the distance, little r. So we're saying that our potential could still be approximately central, perhaps, approximately independent of angle, even in quite a complicated atom. And that would mean we would still be able to use the spherical harmonics. We would still approximately, at least, be able to separate our equation for a more complicated atom into something that has spherical harmonics for the angular part and some other function we've not yet figured out for the radial part. But these spherical harmonics would still be the first approximation to the angular form of the orbitals, even in a more complicated atom. That means that we could still use, at least as a first approximation, the hydrogen atom labels for the orbitals even of more complicated atoms. That is, the s, p, d, and f labels. And that's exactly what we do. Even for more complicated atoms, we can still use these labels here, at least as a first approximation, for talking about the various orbital states in complicated atoms. And that's because we can approximately say, at least as a first approximation, that even in a complicated atom which has lots of electrons in it, the potential is still approximately independent of angle.